So in the previous video, we have learned about the chemistry of carbohydrate and the classification of carbohydrates like monosaccharides, disaccharides, oligosaccharides, and polysaccharides. And we have learned that polysaccharides can be of homopolysaccharides and heteropolysaccharides. We have covered the homopolysaccharides part in the previous video, which you can see in the card box. And today we are going to learn about the heteropolysaccharides. So heteropolysaccharides are the polysaccharides which contain different monosaccharide units. Different monosaccharide unit, or you can say more than one monosaccharide units. Which are different. Okay. These are also called as heteroglycans. Heteroglycans. And the example of heteropolysaccharides are agar or agarose, pectins, and mucopolysaccharides. Okay. So now we'll see what is agar. So agar. What is agar? This agar is a heteropolysaccharide which is formed from seaweed. Okay. And it consists of glucose, galactose, other sugars, and inorganic sulfate group. So this agar contains glucose, galactose, other sugars, and inorganic sulfate. This inorganic sulfate, it contains negative charge. So because of this inorganic sulfate which contains negative charge, this agar itself gets a negative charge. Okay. Now this agar is used as solidifying agent. In bacterial culture or culture of bacteria in microbiology. And it is also used as matrix for electrophoresis and supporting medium in immunodiffusion. So this agar acts as a solidifying agent in the culture of bacteria. And why it is used as a solidifying agent? Because bacteria cannot digest agar, so it can easily be used as solidifying agent. It also used as a matrix in electrophoresis, and it is also used as a supporting medium in immunodiffusion. Electrophoresis and immunodiffusion will cover in our future videos. Okay, so let's see now what is agarose. Agarose is formed from the agar itself. What is the difference? That it contains same composition like glucose, galactose, and other sugars, but it lacks inorganic sulfate. So there is no inorganic sulfate. There is no inorganic sulfate in agarose, and because of that, it does not contain negative charge. Okay. So because there is no inorganic sulfate in agarose, it has no negative charge, and it is also both agar and agarose are alternatively used for the matrix in electrophoresis and supporting medium in immunodiffusion. Now we will see mucopolysaccharides. This mucopolysaccharides are also known as glycosaminoglycans. They are also known as glycosaminoglycans. So this is a mucopolysaccharide. Mucopolysaccharides, these are also called as glycosaminoglycans, and these mucopolysaccharides, they are mainly composed of uronic acid and amino sugar. So main component of mucopolysaccharides are formed from uronic acid and amino sugar. So let us first understand what is uronic acid and what is amino sugar. Okay, so as you can see here, this is a normal glucose molecule. You can see a D-glucose, okay, which has aldehyde group as a first carbon atom. So what is this? How you get uronic acid? So these reactions, how you get uronic acid, these are called as oxidation of sugars. Okay. So when there is a mild oxidation stage, then what happens? That this CHO group is getting replaced by carboxylic group. Okay, COOH. Okay, and then we get aldonic acid. But sometimes what happens that the CHO group is preserved. That is, it somehow is protected, and because of that, the CHO group cannot be replaced by carboxylic group, and in that situation, the last carbon atom of glucose, which is CH2OH, this last carbon atom gets replaced by carboxylic group. Okay, so as you can see here, the aldehyde group is there because it is protected, and the last carbon of glucose get replaced by carboxylic group, and then in that way we get uronic acid. As this is a molecule of glucose, we get glucouronic acid. Okay. So this is how you get uronic acid. So glucouronic acid, as there is galactouronic acid and malonic acid. Okay. Okay. Now we'll see how we get the amino sugar molecule. Okay. So this is again glucose. Okay. This is again glucose molecule. Okay. What happens is that on second carbon atom of hexoses, normally it is the second carbon atom of hexoses, as in this case that is glucose. The second carbon atom of glucose, the hydroxyl group which is present, this hydroxyl group, it gets replaced with amino group. Okay, so this amino group replaces hydroxyl group, and we get glucosamine. So this is called as glucosamine. Okay, so we get amine. Okay, as amine group is attached to the second carbon atom by replacing hydroxyl group. Okay, and if the further acylation reaction happens, then it gets converted into next product, which is N-acetyl glucosamine. Okay, so this is N-acetyl glucosamine. So what do you mean by acetylation? So acetylation means addition of acyl group. Okay, acyl group. What is the commonest acyl group? Is CH3CO. Okay, so the process happens in that way that the glucose molecule, on the second carbon atom of glucose molecule, the hydroxyl group gets replaced by the amino group, and it converts glucose into glucosamine, and the further acetylation, that is addition of acyl group, which is commonly CH3CO, we get N-acetyl glucosamine. Okay, so So this N-acetyl-glucosamine along with glucuronic acid, these are the main components of mucopolysaccharides. So now you understood how the uronic acid and amino group forms, and now let's continue with our discussion of mucopolysaccharides. So we'll see the examples. Examples of mucopolysaccharides are hyaluronic acid, then we have chondroitin sulfate, we have heparan sulfate, then we have keratan sulfate, and we have dermatan sulfate. Okay. So now we will see them each one individually one by one. First we will see hyaluronic acid. Okay. So hyaluronic acid is a kind of mucopolysaccharide which consists of mucouronic acid with N-acetyl glucosamine. Okay, so it consists of glucuronic acid and N-acetyl glucosamine, which are linked together with the help of beta 1,3 and beta 1,4 glycosidic bond. Okay, and this hyaluronic acid, acts as ground substance. It acts as ground substance in joints, synovial fluid, then vitreous humor of eye, and in it is also present in connective tissue, and tendons. Okay, so it acts as a ground substance in joint, synovial fluid, vitreous humor of eye. It is also present in connective tissue and tendons. Okay. It forms gel covering over wound. Okay, so it forms a gel-like cover over the wound. It is also acts as shock absorbent. It also acts as shock absorbent in joints. Okay, so it acts as a shock absorbent in joint. Then there is an enzyme called as hyaluronidase. Okay, so there is an enzyme called as hyaluronidase. This hyaluronidase enzyme, what it does, it breaks down beta 1,4 glycosidic bond. It breaks down beta 1,4 glycosidic bond which is present in hyaluronic acid, and it can also break down this bond in other kind of mucopolysaccharides. Okay, and it is present mainly in testes and seminal vesicles. Okay, so this hyaluronidase enzyme mainly present in testes and seminal vesicles. Again, what is the other function? The hyaluronic acid which forms the gel around the ovum, this hyaluronidase destroys that gel-like covering surrounded ovum. How that is happening? As this hyaluronidase it is present in the head portion of the sperm. There is a cap over the head portion. That cap contains hyaluronidase, and whenever that cap or head of the sperm gets in contact with the outer layer of ovum, which contains hyaluronic acid as a gel, this hyaluronidase degrades that beta 1,4 glycosidic bond in hyaluronic acid and break downs that gel covering of ovum, so that helps to that helps the sperm to penetrate the ovum better and helps for the fertilization process. Okay, so it helps fertilization. Okay. Next one we are going to see is preparing for heparan sulfate. Heparan sulfate consists of N-glucosamine 6 sulfate with L-hyaluronic acid. Okay. So heparan sulfate mainly consists of N-glucosamine 6 sulfate. 6 sulfate is this sulfate molecule present on 6 carbon atom of glucose, and L-hyaluronic acid, which are linked together with the help of alpha 1,4 glycosidic bond. Now, what is the use of heparin? Okay, it acts as an anticoagulant. Which means it prevents the formation of clots. Okay. So, how this heparin does its work as an anticoagulant? So, first of all, it activates antithrombin 3. Okay, it activates antithrombin 3, which in turn inhibits thrombin. This thrombin molecule, what it does, that it converts fibrinogen into fibrin. This fibrin is a substance of coagulation. Okay. So, this thrombin, what it does is converts fibrinogen into fibrin, and by inhibiting this thrombin molecule, antithrombin 3, what it does that it prevents formation of clot. Okay. Also, heparin acts as it inactivates some clotting factors like factor 2, 9, 10, 11 and factor 12. So it inactivates factor 2, 9, 10, 11 and 12. So because it inactivates this clotting factor, it prevents formation of clot. This heparan sulfate, we can see this in lungs, in liver, in spleen, and in monocytes. And the commercialized version, heparin, which we use in medical practice day to day, is produced by animal lung tissues. Okay. So what is heparin sulfate? It consists of N-glucosamine 6-sulfate with hyaluronic acid, and these both molecules are joined linked together with the help of alpha-1,4 glycosidic bond. Heparin or heparin sulfate, it acts as an anticoagulant by two ways. It activates antithrombin 3, which inhibits the thrombin. By inhibiting thrombin, it inhibits the process of formation of fibrin from fibrinogen. If it inactivates factor 2, 9, 10, 11, and 12, and it prevents the formation of clot. This is found in lungs, liver, spleen, and monocytes. And the commercial heparin, which we use for the medicinal purpose in day-to-day life, it is obtained from the animal lunch. Now we'll see chondroitin sulfate. This chondroitin sulfate mainly composed of glucosamine, glucouronic acid, and galactosamine 4-sulfate. Okay. This chondroitin sulfate consists of glucouronic acid and galactosamine 4-sulfate, which are linked together with the help of beta 1,3 glycosidic bond and beta 1,4 glycosidic bond. So this chondroitin sulfate, it is made up of glucouronic acid and N-acetyl galactosamine 4-sulfate, which are linked together with the help of beta 1,3 and beta 1,4 glycosidic bond. This chondroitin sulfate it helps to maintain the shape and structure of tissue. And which kind of tissue? It is present in cartilage. It is present in cartilage, connective tissue. It is also present in cornea. It is also present in skin. Now we will see keratin sulfate. Okay, keratin sulfate. And this is the only mucopolysaccharide which does not have uronic acid. Okay, so no uronic acid. Okay. This is the only mucopolysaccharide which does not contain uronic acid. So what are the contents of keratin sulfate? So mainly galactose and N-acetyl glucosamine. Okay. And this keratin sulfate, main function of this keratin sulfate is to help cornea keep transparent. So it keeps cornea transparent. And this galactose and N-acetyl glucosamine, those two are linked together with the help of beta 1,4 glycosidic bond. 1,4 glycosidic bond and beta 1,3 glycosidic bond. Now we'll see dermatan sulfate. Dermatan sulfate consists of N-acetyl galactosamine with L-hyaluronic acid. which are linked together with the help of beta 1,3 glycosidic bond. And this dimethyl sulfate, it is present in blood vessels. It is also present in heart valves, and it is also present in skin. And this dimethyl sulfate, it helps to maintain shape and structure of tissue. Okay, so we have seen in today's video heteropolysaccharides, which are hyaluronic acid, dimethyl sulfate, chondroitin sulfate, keratan sulfate, and heparan sulfate. So I hope the concept is clear behind the mucopolysaccharides and all around the polysaccharides. So in the next video, we are going to see isomerism of carbohydrate. So see you in the next video.